We're moving on to a new kind of derivative called implicit differentiation. So we are going to be using implicit differentiation in different types of problems, most specifically related rates and optimization. So before we move on and start to actually do some examples and talk about what implicit differentiation is, I think it's important that you know the difference between implicit and explicit, which is what we are used to doing. So if you just do a quick Google search, you'll see that implicit is indirect, but explicit is direct. And I think that when you see the types of examples that we're going to be doing, you're going to see why that definition makes sense. Here I have a couple of examples. So our first example, again, is what we're used to. So it's our explicit equation. And what you see is that this is direct. Our equation says y equals something. It's going to be very easy for us to calculate y prime or dy by dx because it already says y equals. If you take a look at the second equation, our implicit equation example, it says x squared plus y squared equals 64. It's not so easy to do the derivative for this equation, which is a circle, by the way, in case you recognize that, because it's not specifically saying y equals something. We are going to be going through some examples, and I am going to be showing you how to do this in this lesson. In our first example, it says that we are going to find the derivative of xy equals 1, both implicitly and explicitly. So I know I've said this before, but I'm going to say it again. Explicitly is what we're used to. So we know that in order to do this, our equation needs to be in the form y equals. So the first thing that I'm going to do is I'm going to rewrite this so that it's a y equals. So y is equal to 1 over x, which I know that I'm just going to rewrite as x to the minus 1 because then it's a lot easier for me to derive. Now, if I'm going to derive this, y prime, or dy by dx, is equal to negative 1x to the minus 2. And I don't know why I have a dy by dy here. Dy by dx is equal to negative 1 over x squared. We're now going to derive this implicitly, and so I am going to be showing you the steps, I guess, and there is a major difference. So if you're not following along perfectly with this one, that's okay. I'm going to go through a couple more examples. So what we need to do now is we need to take the derivative with respect to x of xy, and we need to take the derivative with respect to x of 1. Notice how I'm just saying d by dx. I'm not saying dy by dx anymore because I'm not taking the derivative of y because I don't have a y equals equation. So the next thing that I'm going to see is that I have a product rule in here. I have an x times a y. I need to go ahead and use that product rule that I know. So I'm taking the derivative with respect to x of x times my y, plus I'm taking the derivative with respect to x of y times my first function x. Give me 1 second. It's a little bit too big right there. All right. And that's going to equal the derivative with respect to x of 1, which is a constant. And we know that the derivative of a constant is always 0. In my next step, I can go ahead and start taking those derivatives. So I'm taking the derivative with respect to x of x, which we know the derivative of x with respect to x is 1. And then I'm going to be multiplying by my y, plus the derivative of y with respect to x. Now, we can't take the derivative of y with respect to x, so what it's going to leave me with is dy by dx times this original x. Now, this is good news because we know that my end goal is to get a dy by dx. Now at this step, since we know we want it to equal dy by dx, I am going to rearrange this equation and isolate that dy by dx. So I will bring this 1y over, and then I'm going to be dividing both sides by this x. Now I know what you're thinking, and you're probably thinking, hold on, that is not the same as what I have on the left-hand side or in the explicit differentiation. But it is if we go one step further. So if we look back at our original equation, or even this first line that I have here, we know that y is equal to 1 over x. So if I go ahead and I plug 1 over x in for my y, I'm going to be getting a negative 1 over x all over x, which I know is the exact same as a negative 1 over x squared, which is the exact same thing that I got when I derived it explicitly. The next couple of examples are going to get a lot harder, and so our first one says find the derivative for each. X squared plus root of y is equal to x squared y cubed plus 5. Now, as you can see, what I did here was I just changed that root y to be y to the 1/2 because we know that makes it easier when we're deriving. Now when I look at this, I know that I'm going to be using implicit differentiation because my y is not isolated. It doesn't say y equals. So I'm going to go ahead and I'm just going to start deriving. So the derivative of x squared is just 2x. And the derivative of y to the 1/2 is 1/2 y to the negative 1/2. But I didn't derive with respect to x here, so I need to make sure that I'm putting a dy by dx beside that. Now, at the right-hand side, I'm seeing a product rule here, so I have my x squared y cubed. So I'm going to do the derivative of the first term, so the 2x times my second term, plus the derivative of the second term, so a 3y squared. Again, that's not with respect to x, so I need my dy by dx times my original first term, and then the derivative of that constant 5 is just 0, so I don't need to write anything. My goal now is to isolate dy by dx, so what I need to do is I need to take any term that has a dy by dx and move it all to the left and move everything to the right. So as you can see, I've moved the two terms that have the dy by dx over to the left, and I've kept the two terms without on the right. One thing I did want to notice before we move on, you will notice that this second term does look a little bit different. So I have combined the 3y squared with my x squared and put it in alphabetical order just so that it looks nice and tidy. Now remember, my end goal is to get this dy by dx by itself. Since I have two of them, it only makes sense that what I'm going to do next is common factor out the dy by dx in these first two terms. And now that I've common factored that out, if I want to isolate my dy by dx, I will be dividing both sides by this term that I've common factored, which is my answer here. And then if I just wanted to tidy it up even just a little bit more, I know it's not good form to leave any negative exponents, and so I could just move this y to the negative 1/2 with my 2 as a root y. Here's our second example. In this example, I am going to do things a little bit different. I am going to start off by giving you the first line and working through that with you, and then I'll give you the final answer. So I'll leave that up to you to do the simplifying in the middle. If anyone gets stuck or can't figure it out and wants a full solution, please don't hesitate to ask me for that. So we're going to start off by deriving the first term here, and since it has an x, it's just going to be our normal derivative. So we will get 6x. Plus, the derivative of y squared is 2y, but since it's not x, we're going to be using or adding a dy by dx. The next thing that I notice is a product rule, and more importantly, there's a minus sign here. So I need to be subtracting and adding the bracket in so that when I do the product rule, I remember the negative needs to be distributed through both terms. So the derivative of 2x is going to be 2 times my second function, which is y, plus the derivative of y, which is just dy by dx, times my original function of 2x. Now, if you wanted to do this a little bit differently, you could. I assumed that this was my first function and that this was my second. There are multiple ways to do this. Plus the derivative of 2x, which is just 2, minus the derivative of 4y, which is 4 dy by dx. And I'm running out of room here, but the derivative of 10 is just 0 since it's a constant. So I'm just going to go ahead and add this in here so that you can see it a little bit easier. Now, at this point in time, I think that if I were you, I would be pausing the video and just attempting to isolate my dy by dx and solve this. But I will give you the final answer, and like I said, don't hesitate to ask if you get stuck. And here's that final answer. Our last example says, find the derivative with respect to r for the volume of a cylinder. Now, if we think back, maybe you can remember the formula for volume of a cylinder. Maybe you're going to have to think a little bit harder about it. But the formula for volume of a cylinder is the area of the base times the height. So the area of the base is a circle, so pi r squared times our height. Now, if we go ahead and we derive this with respect to r is not isolated. We're using implicit differentiation, and we're going to go from here. So the derivative of v will be dv by dr. Now, when I look at this, I know I have a product rule. So I have my first function here, because remember, pi is just a constant, and my second function will be h. So when I derive this first function, I'm going to get 2 pi r multiplied by that second function. And then I'm adding the derivative of the second function, which is just 1, but it will be a dh by dr because I'm not deriving r, I'm deriving h, multiplied by that original first function, so the pi r squared. Now, in this question, this is as far as we could go. Later on, when we're talking about related rates, I might be giving you maybe your dh by dr, or I may be giving you information about an r equals or an h equals. But like I said, for now, this is as far as we can get.